the controllability of ship in water and the equations of ship motion. This is article number 12.5 from the book Mechanical Systems Calculations of the Marine Facilities. We will consider today the presumptions and the approaches to calculate the elements of the motion of ship in still water. For today, we will consider this motion with not control. The properties of ship seaworthiness includes the ship controllability. Ship controllability consists of separate segments, not separate but independent segment. We can consider the ship property to move along the straight line means its sustainability on course, and the ability to move along controlled current trajectory is the ship turning ability. So we have like two properties: the ability of ship to move along the straight line, and the ship turning ability to opportunity to move along the controlled current trajectory. Property of ship controllability methodologically also covers maneuverability. Maneuverability, which means the ship opportunity to change the motion elements under certain velocity. To fulfill the property of controllability, ships are equipped with the controls. Equipment and machinery of ship control are distributed methodologically into two groups, the main and auxiliary ones. There is also a group of limiting controls. Main device includes the steering devices, as well as the propulsor and propulsion steering ones. On the draft 12.5.1, they are performed the samples of the propulsion steering devices of the ship. On the left, 12.5.1a, we see the rotary propulsion steering columns. Rotary propulsion, the gearbox here is a hand gondola, and on the right we have the azipods. In the azipods and the gondola inside located the motor, electric motor. Here we have the gearbox, the motor. The device is rotated. So this used as for the propulsion of ship as well, for ship control, maneuvering or control on the straight line when the ship moves along the straight line. Sorry, again. When you consider the motion of ship on still water, we can describe this by a system of equations in three projections, considering the necessary assumptions. So we can just consider the ship motion on the surface of the water. So three equations corresponds to the degrees of the ship freedom on the surface of the ocean. So the first equation is the equation which corresponds to the forces, to total forces acting on ship in the component projection on the longitudinal direction abscissa of the initial coordinate system associated with the ship. We have a Cartesian coordinate system associated with the ship to do the calculus of ship controllability. Yeah, we have here the characteristic of the ship inertia. In the first brackets, delta uppercase is the displacement of ship. Mu with the index is 1. 1 is the added mass of ship when it moves with acceleration along the abscissa axis. Abscissa axis we indicate usually as the x ordinata y and applicata z, but for the system of the coordinate associated with the ship, we can indicate by the Greek lowercase letters like she, eta, and the chi, for example. Okay, return to the equation. The second sum, I mean the subtractant is as well the characteristics of ship inertia and displacement and added moment of added mass of ship when it moves with acceleration along the ordinate axis. Ordinate axis. Y is transverse motion of ship. So this is the acceleration. This is a product of the transverse velocity of ship. So we do not consider the coordinates of the motion themselves, but in the equations we consider the velocities and accelerations. Accelerations are derivatives of the velocities, such as this is acceleration of ship. The first derivative of the longitudinal velocity of ship, this is the first derivative of the transverse velocity of ship, of the acceleration of ship along the coordinate axis y. And the product by omega z. Omega z is the cyclic velocity of ship rotation around the applied axis. Minus mu 2,6. This is a factor. I cannot say definitely what is that, added mass of water or added moment of the inertia, but this is just factor in the general set of the equations of the interdependence of ship two motions, rotation around the ordinate, rotation around the applied axis, and the ship motion due to the direction of the rotation around the applied axis and the motion along the ordinate axis. This is a second factor. Just factor to the squared angular velocity of rotation of ship around the applied axis. So when we watch on the equation very attentively, this looks like just a component of the rotation acceleration of ship when it moves around the circular trajectory, directed to the center of the trajectory. And this is we go to the details. As well, the acceleration of the ship rotation around the definite axis. The second equation is a projection of all forces on the applied on the applied axis y. So velocity, the first derivative of velocity along the axis y, the first derivative that is acceleration. This is displacement of ship. This is added mass of water. Characteristics of the inertia of the ship in the water when it moves along the ordinate axis. The second is the added mass of water when it moves along the abscissa axis, and the velocity, and when moving to the bowward. And this is angular velocity rotation around the applied axis, and the same the characteristic of rho by the influence of the rotation around the applied axis on the forces, which is characteristic when the ship moves along applied axis. The third question is the first two questions are equals to the driving forces, or projection of all driving forces on the abscissa axis, projection of all driving forces on ordinate axis. On the right, on this equation, we have the projection of all moments, driving moments applying to the ship, not external moments. So when consider the controllability of ship, we have on a side to the ship action of the external forces and moments of these external efforts. Actually, external could be those which are independent on the action of the ship itself, implying the controllability of ship, and the driving forces, which is the action of the ship controls and ship external forces. This is driving forces, external, but acting on behalf of ship, not unpredictable external forces, which is available probably as well. Total of the moments, driving moments acting on the ship around the applied axis. This is the moment of the inertia of the ship rotation around the applied axis. This approximately, we consider the ship is the length is much bigger than the ship breadth, so we can consider the moment of the inertia of ship rotation around the applied axis itself, ship rotation, comparable with the moment of inertia of ship rotation around the ordinate axis. So it's about the same as I with the index y could be moment of the inertia of ship rotation around the applied ordinate axis. The same as about the moment of the inertia of ship when rotates around with acceleration around the applied axis. These two about equal moments is due to the assumption that the ship breadth and depth incomparably smaller than the ship length. And and the ship load and its masses distributed along the length. The second summand is the acceleration with the of the ship when it moves the translationally along the ordinate axis with the moment of the inertia, which we call we have the concept of the reciprocity of the moments of the added masses of the inertia within the matrix. When we have two indexes, this means that this is element of matrix with the lines, with the rows in the matrix, and with the columns. The rows corresponded to each equations in the system of the equations, and the columns corresponded on the interdependence from what direction the ship motion impacts for definite one direction considered by the first index in the for the masses, added masses, the same as for the damping coefficients. And next minus the difference of two masses. First is the added mass of the ship when it moves along the ordinate axis with acceleration, minus the added mass when the ship moves along the abscissa axis. There's two masses here in the first two equations, multiplied by the ship velocities, one and second one, when the ship moves along the abscissa axis and ordinate axis, plus the as well the interdependence of two rotations of ship around or two motions of the ship, rotation around the applied axis with circular velocity omega, and the translational motion along the abscissa axis equal to total the moments. As well, we can, in the associated with the ship Cartesian coordinate system, define the components of the velocity as the and as well the angular velocity and translational velocities too on the surface of the ship on the surface as the first derivatives by time of the coordinates in the ship motion in the associated system. So if the ship is associated, so we cannot determine the coordinates of the ship motion as the associated system. This is in the fixed coordinate system in which we can find the trajectory of ship motion. But in the associated coordinate system, we can find the velocities and accelerations. And here we have only velocities. We do not have the displacement in this associated with the ship coordinate system. Besides, I will not go into details how to find these equations, because within the concepts of the calculations of the mechanical systems, first of all, we have to consider the methods how to do the calculation of these equations. We have three equations of the ship motion on the surface with controls. If the right sides of driving forces nx and y, these forces, components of forces on the horizontal axis of the Cartesian coordinate system, transverse axis, and the longitudinal axis, projections of the force driving the rotating moment around the vertical axis that is rotating in the plane, in the horizontal plane. We just would like to do the study how to do the decision of these equations. First of all, is logical to do the definite simplification. We have to assume the prerequisites, some requisites, and simplify the prerequisites, and to do the simplification. First of all, that while considering the ship motion in the horizontal plane, that is motion by the direct or straight or the curvilinear trajectory, we assume that the ship velocity along the abscissa axis associated with the ship would be constant. It's logical. For the nonlinear subjective, we consider not so much important maneuvers of the ship, not impacting so much on the longitudinal ship velocity. So in this case, if we would have the decision with a tremendous exchange of ship velocity, in this case, we have to just redefine the prerequisites and to do the another one calculation. Indefinite one calculation, when we're using these equations, probably we'll consider that the ship velocity along abscissa axis associated with the ship will be constant. So the time derivative has to be zero. So this first sum and the equation have to be zero. Another one, we assume that the ship, we have to assume the ship smallness of breadth and depth and draft if compared with the length. So this the ship very like a very long physical body very long. And besides, we will as well assume the symmetry of ship related with the longitudinal axis and the transverse axis. This makes us possible to consider the other types of ship motion on the surface independent, as well as we did for the study of ship rocking. We did it more precisely in the article 12.1. Yeah, but here the research of the motion of the ship under controls, or with not controls, with the zeros of the right side. What we will do in the next and this definite one article. We will consider the symmetry of ship as the assumption. If the ship is symmetry, the matrix of the edged masses have to have the diagonal form of the matrix. If diagonal, only we have to remain only indexes of one number. So this will be mu1 only, mu2, mu1, mu2, and the edged masses or edged moments of the inertia with other indexes, so independence on the ship motion in other directions have to be zeros. So we have the first sum and zero due to the ship moves with a constant longitudinal velocity. We have the last sum and zero due to the ship we assumed as symmetrical by the diametral plane and by the midship plane. This is zero as well due to the mu 260. This is zero as well, mu 260, and this is zero as well. So, and besides, we will consider a ship of motion with a constant velocity. That's why we will consider only as the subject of decision of the differential equations. We consider only two equations of the oscillating equations of finding of the elements of the ship motion on the surface, with not considering longitudinal motion, as in the next we can find the longitudinal motion characteristics having these two. If we just assume that the velocities of ship motion longitudinal have to be constant, So this is a differential equation from the system after the discussed simplifications. And to solve this system of the equations, first we have transform the first one equation. We have derived the acceleration y from this equation. So we remove the second sum to the right side of the equation, and we will divide this equation by the denominator displacement and the mass. We have just only one index due to we do not consider the interdependence of other motions. We consider isolated motion, longitudinal, transverse, and rotational motion on the surface. And we have to differentiate the second equation. This is one second equation to find the second derivatives, yes. And from this summand, we theoretically we have two summands having derivatives of the product of these two functions, but the derivative of this first one function has to be equal to zero due to we assume that the ship velocity along the abscissa axis do not vary, remain the same. It is an approximation, yes, but likely to do the decision of these equations. And after definite transform, when we substitute the first one equation into the second one here, this decision on the right side here instead of the y acceleration of the ship motion along the ordinate axis with first derivative, that is acceleration. We substitute here, and next we have the second order inhomogeneous linear equation of the ship rotation with only one variable function subject to find the omega z at the velocity of the rotation of the ship around the applied axis. This is the equation. This equation in homogeneous have the right side, these controls. So we have perhaps we have the rudder, as we, for example, can consider the ship with the stern rudder. And the rudder, when we turn it, caused the transverse force. Transverse force here came from here. And the moment rotating the ship around the moment rotating the ship has the first derivative as we got the the second equation. The moment rotating the ship around the applied axis. Okay, this equation decision in accordance with the Gauchy problem. We can perform as a total of two summas. The first sum is a general decision of the appropriate homogeneous second order linear equation, differential equation, plus the particular decision of the inhomogeneous equation, of this inhomogeneous equation. But in this case, we will, in this definite one article of the book, we will consider the motion of ship is not controlled because it will be the subject of the interest of finding the own properties of ship, of the motion sustainable by the straight trajectory or just the moves with oscillations, or just we will have the unstable motion of the ship on the surface as a property of the ship itself. It's of the interest to find is the ship stable on course by the straight motion or not stable, and what kind of the instability we can face. So we will consider this equation decisions with zero right side, with the transverse force rather just is in diametrical plane. So the feedback treatment system is not active. So for this equation, we have the homogeneous with the zero right side equation of the ship motion with not control on still water. This is kind of the general decision of this one in homogeneous equation with a definite right side. But this is the second is a homogeneous equation. Homogeneous equation, and P is characteristic number. P squared is a number of this one factor. This one factor together we can consider as the characteristic number of the second order linear homogeneous differential equation of the ship motion by the parameter of the angular velocity of rotation around the applied axis when it moves. So what we can have as the general decision of this homogeneous second order linear equation of the ship motion with not controls. We assume zero controls of inputs. We have the roots of characteristic equation. These roots of the characteristic equation we can find as plus minus multiplied by the square root of the fraction in the numerator. We have two factors, added mass of water when the ship moves with acceleration, the characteristic of the ship inertia along the transverse ordinate axis is added moment of the inertia when the ship moves along the abscissa axis. And this is the uppercase delta displacement of ship as well, the added mass when the ship moves transversely. When the ship moves along the abscissa axis, this is when the ship moves along the ordinate axis, and the in denominator and the total of the ship inertia when it rotates around the applied axis. What can be the decision considering these characteristics equation roots? It depends on is the decision real number or just imaginary number. So we have here plus minus from this velocity Vx squared factor on the left part as a part at the same time of the homogeneous equation. Due to this is inhomogeneous, but we assume the absence of the controls action. And for the homogeneous, if the right side is equal to 0, we have the decision plus minus Vx. So if the real roots and imaginary roots of the characteristic equation could be positive or could be negative. This impacts just on the theoretical form of the decision, but from the physical assumptions. I will not go in the deep to explain how does the negative roots will impact the decision, but it is not in the interest due to this in the practical needs. In practical needs, we are only interested in the decision of the ship motion with not control. That is a homogeneous second order differential equation with the positive magnitudes of the characteristic number. I will a little bit explain and after why we are of the interest of the just only the positive decisions of the characteristic equation. Yes, and if we have the real number, the decision, the general decision of this one, the omega z1 is will be as well. We'll have the type like C1, the constant, depends on the initial conditions, product by E, Euler number, in the power to P, the characteristic number, multiplied by T, plus C2, product by E in the power minus P by T as well. If the P is a real number, so P in square degree more than 0. And if the P in the square degree less than 0, then we have the imaginary number. And in this case, we will have the trigonometric form of the general decision of this homogeneous equation of the ship motion on the surface. That is the angular velocity of ship rotation when it moves with not control will be equal to the two summands with the first factor and second factor as a constant of the integration and the cosine and sine trigonometric functions when the p squared will be less than 0. That is, the p is imaginary number. So if we will substitute the initial conditions, what can be initial conditions? When t equal to 0, the angle, the velocity of the rotation will be equal to 0 numbers, omega z0, and the acceleration will be equal to the omega first derivative z0. So after the substitution, they got general decision of the homogeneous second order equation of the ship motion on the surface with not controls, and by the element of the motion, there is the velocity of the angular rotation around the applied axis. We can have the decisions in two types. The first type corresponded the real number of the decision of this homogeneous equation. Second is for the imaginary number. The exponential, if the decision of the characteristic equation is real, or the trigonometric the decision is imaginary. This trigonometric decision with the defined and substituted constant C1 and C2 in each of the equations. And other possible designations for the good decisions. Yes, so after some transforms, we can define the considering these equations and after transforms, when we derive the common factor out of the brackets, we can find the decision in the indicated form. This is a fraction, indicates the proportion between the ship angular acceleration to the initial angular acceleration of rotation of ship around the applied axis. This depends on time. And we can designate the use of the hyperbolic functions. We have two hyperbolic functions in math known in math as a sine hyperbolic and cosine hyperbolic, as the sine hyperbolic is a fraction of E in the definite to the power x minus e to the power minus x divided by 2. And cosine hyperbolic is a fraction in numerator e to the power x and plus e to the power minus divided by 2. This is cosine hyperbolic. This is just only the opportunity available in math how to change the designation. Just a little bit compact form of the got decision of the linear homogeneous second order differential equation of the ship motion with not control. So if they consider the functional element of the angular velocity of the ship rotation with not control around the obligate axis. Okay, let's consider just example. In the article 12.3, we did consider the ship. We just only take the characteristic of the ship, the length, 160 meter breadth, 20 meter the depth, 11 meters the average draft at loaded waterline, 5.2 meter the displacement of the ship is 9,150 ton. The general completeness coefficient, that is the proportion between the ship submerged volume and the volume, the parallelepiped with the sizes of the ship, length, breadth, and draft. This proportion will be of the ship volume to this volume of this indicated parallelepiped will be is 0.74. Waterline area completeness coefficient C alpha is 0.89. That is the proportion of the ship waterline area to the area of the rectangle with the sizes of the ship breadth and length by the waterline. The ship operating velocity 13.6 knots is equal to 7 meters per second. And we consider this is a ship. This is a LNG, liquefied natural gas bunkering tanker, the ship of the modern type, very good ecological. So we as well assigned the initial conditions. The initial angular rotation velocity of the ship around the application axis would be 0.1047 the radian per second. That is within the velocity of the ship. The ship makes 2p turns for just only 1 minute. 2p is one round turn. The ship did for just only 1 minute 60 seconds. For this definite magnitude of the initial velocity. It is assumed that we have definite logical proportion between the initial angular velocity and the initial angular acceleration, because as the formulas for the velocities angular independence on time usually consider the factor to the time as a p, the characteristic number from the decision of the homogeneous equation. This one homogeneous equation, a linear second order homogeneous equation, we have a p factor to the time as well as in the trigonometric form for the imaginary magnitude of the root of the characteristic equation at the same time as for the and as the same time for the exponential type of decision when the root of the characteristic equation is more than 0. So in this case, when we will have to consider the derivative, time derivative of the angular velocity to have the angular acceleration, it's logical to assume that perhaps the magnitudes of the initial angular velocity and initial angular acceleration would be equal to the this one characteristic number, magnitude. So this is the characteristic assumed of the initial angular acceleration. The use of the amplitude as a factor to the initial angular velocity when finding the acceleration indicates like the indicates like I'm sorry. Here we have to consider the first derivative. The first derivative, exactly, yes. Sorry for the just error. Here the first derivative of the just error in the description of this formula. The acceleration is the first derivative of the angular velocity. Oh, no. We have the second derivative as well. Yeah, excuse me, the second derivative. Yeah, this correct. This correct. Just I a little bit doubted about is it correct the second derivative of when finding. This is not angular acceleration. This is second derivative of the angular velocity. Yes, and but between the angular velocity for continuous motion of ship and angular acceleration, this is usual to consider the factor of the P jet decision of the characteristic equation. This is correct found the characteristic, yes, not the errors. I just a little bit dubbed and returned to consider. Am I right or not? And besides, to find the characteristic root of the second order linear differential equation homogeneous, we will use the empiric formulas. Originally, we did it in the article number 12.2 in the more details, but the moment of the inertia of the ship rotation around the applied axis, the self moment of the ship, not the eddy mass moment, have to be equal approximately to the moment of inertia of ship rotation around the ordinate axis, and we can use the empirical formula that depends on the general of the completeness of the waterline area and the ship displacement and the squared the length of ship waterline. Otherwise, just substitute. We got that probably the moment of inertia of ship rotation with acceleration around the applied axis will be equal to 7,122,651 ton by square meter. The eddy mass of water, we assume for definite one calculation is presumably half as well, using the approximate empirical formula. That is about 50% of the eddy mass of when the ship heaving. So we considered previously the ship heaving in the article 12.3. We consider the ship heaving, and in the article 12.3 and article 12.2. And for the ship heaving as a main type of the ship motion in the water, which are characterized by the restoring forces and moment. It says ship rolling, the ship pitching, and the ship heaving. Only 3 of 6 available in the space for the ship motions are characterized by the restoring forces and moments. For these main types of the ship rocking, we consider the eddy mass when the ship moves with the acceleration in heaving along the vertical axis. But we assume that when we consider the ship moving with acceleration along the ordinate axis, that the eddy mass of inertial water would be just 50% of the eddy mass of the water when the ship moves along the vertical axis. This as transverse motion along the ordinate axis, as a transverse motion along the applied axis. Both two are transverse motions of ship. But we have the eddy mass when the ship moves in the directions of side with acceleration to port side or to starboard. From side to side it moves. This will be twice less than it moves upward and downward in the oscillation. So we have mu2 as a 0.5 produced by mu3, 0.5 displacement of ship. This is an empirical formula we used in the article 12.2. And after the substitute of this factor of the completeness of the waterline, factor of general completeness of ship and displacement of ship, etc., we can have 4.009 ton. This is eddy mass when ship moves with acceleration in water along the ordinate axis, transverse axis. So the ship itself has the displacement 9,150 ton, this is characteristic of the ship inertia in the translational motions with acceleration. And when the ship is in water, we have to add as to the mass of this characteristic of ship inertia 4,009 ton. And the attached moment of inertia is when the ship rotates, oscillated, we have only one index around the applied axis, is we assume just a half of the moment of inertia when the ship rotates in pitching as well, one of main types of the ship motion, the water with the restoring forces, but the ship in pitching added moment and the moment in yaw, added moment yaw with acceleration will be just only half at the moment in pitching. So after the substitute of the data to that and having the decision by the empirical formula for the ship pitching, item 12.2 for the ship yaw with acceleration, that is when the ship, for the considered example, finding the omega is omega z is angular velocity of ship rotation around the applied axis, we can find that the added moment of inertia is 3,639,000 and 798 ton by square meter. And what we have finally after the substitute on the formula of this for the considered ship, we got the characteristics of its inertia by empirical formulas, and then we substitute this all to the formulas, and first to the formula of the characteristic equation, and that is characteristic equation. We next substitute to the formulas got for finding of the ship motion with not controls on surface of still water, considering the element of the motion as the ship rotation with definite angular velocity. So this equation decision omega z1 for the real numbers of decision characteristic equation, and the imaginary numbers of the ship equation characteristics. So this is the shape of the diagram in 2 dimensions. For example, here is the same diagram, but this is indicated as a parametric diagram on the flight coordinate axis on the plane, in the coordinate plane. This is in 3-dimensional coordinate system, the same diagram as this one. This is on the right, just to explain what is the shape of the diagram. And it's important to consider what are the axes of this diagram. The vertical axis is found the ratio of the angular velocity of ship relative to the initial angular velocity of ship rotation when it moves and on the surface of the ship is not controls angular velocity of rotation around the applied axis. We have one here. We have one this the minimal, the initial proportion of these two velocities, and so in the moment zero when the time is equal to 0, the velocity of rotation equal to the initial velocity of the ship rotation. After the substitute all of the particulars of ship and the variables like time variable here we have as well. And the second variable is the fraction, fraction of the proportion of two added masses. This is the first mass of the ship moving with acceleration along the longitudinal abscissa axis associated with the ship. And the second, in the denominator, we have the added mass when the ship moves with acceleration. It is characteristic of ship inertia in the water impact on the ship inertia when it moves with acceleration along the ordinate axis. And the same fraction is argument of the horizontal axis here. The same fraction is argument as a variable for this horizontal axis. We have two axes. So this is time axis, how do the process develops in the time. This is a parameter axis. What is the interval and magnitudes of the variation of the fraction in the denominator? The characteristics of water impact on the ship inertia when moving with acceleration along abscissa axis. This is in denominator the water impact on the ship inertia when it moves with acceleration on ordinate axis. It's important first more precisely explain what is the horizontal axis. To explain, we will use a table. For the table, we will consider the just range of the variation of this proportion of this added mass when the impact of the water on the characteristic of ship inertia when it moves with acceleration on abscissa axis, and then denominator we have the added mass when the ship accelerates along the translationally along the ordinate axis, and this is considered range. We assign this range, so we consider this proportion in the range from 0.30 to 1.70. And for the definite range, we assume that we have the added mass mu2 is added mass we got by the empirical formula of the ship of the water impact on ship inertia characteristic when it moves with acceleration along ordinate axis, so transversely. For the transverse acceleration, the extra inertia of ship, like the impact on side of the water on the ship. And having the mu2 and considering the range of the variation of this one fraction, we next can consider, we can find what have to be the mu1. So mu1, the added on side of the water characteristic of the inertia of ship when it moves with acceleration along the abscissa associated with the ship Cartesian coordinate system inertial. So the system in which we consider the accelerations and the velocities, and with acceleration we consider the inertial systems moving with the ship. With the system Cartesian associated with ship moves with the ship the same with acceleration as the ship moves, but although in this inertial coordinate system we consider the acceleration available in this system. So the acceleration of ship not depends on is the coordinate system associated with the ship or this fixed coordinate system within the ship moves. All systems are inertial, so with the definition of the accelerations. And having got the added mass when the ship moves along the transverse axis with acceleration, got by the empirical formula I did explain here for the ship when it assigns three particulars, and considering the range of the variation of this fraction of the proportion of two added masses of water, we got the range of the variation of the first one. Mu1 is added mass of the water impact on ship inertial characteristic when it moves along the abscissa axis with acceleration, and this is this proportion we consider as the parameter variation by the second axis here, or as a parameter variation for these ranges if this fraction is between 0.3 to 1 for this one set of the diagrams, and if the fraction is from 1 to 1.7 for this one fraction. This is if the like sinusoid looks. This is for the real roots decisions. This is for imaginary roots decisions of the differential equation we consider here. So for two opportunities when the p squared more than 0, we have exponential decisions. If the p squared is a characteristic from the homogeneous equation of the ship motion on the surface of still water with not controls 0 on the right side, we can have or trigonometric decision or exponential. It depends on, and this is the set of diagrams for imaginary roots of the differential homogeneous equation second order. This we have for the proportion when the mu1 the inertial characteristic from water onto ship proportional to mu2, the characteristic inertia on the ship, impact of water on the ship inertial characteristic moving transversely with acceleration. If this mu1 less than mu2, that's why this one less, that the fraction have to be less than 1. And in this case, the decision of the equation, of the characteristic equation, the root will be imaginary, and decisions will be of the exponential type. And if the added mass will be more in considered range from 1 to 1.7, will be more than the impact of the water on inertia on ship accelerate when the ship accelerates along the ordinate axis. If the mu1 is less than mu2, we will have the real roots p of the characteristic equation, and we will have the trigonometric decision of the linear homogeneous second order equation of the ship motion on the surface with not controls. So after having the mu2, the added mass of ship when moving transverse with acceleration, and after the considering the range of the variation of mu1 relative mu2, having the range of the variation mu1 corresponding to the range of the variation of this one fraction, we can find the two ranges. One range on the left is the range of the real roots of the characteristic equation, and the imaginary roots we have here. For this one sub-range, we will have the trigonometric form of the decision of linear homogeneous second order equation of ship motion with not controls on surface isolated to the element of the motion with a angular velocity of the rotation around the applicant axis. And for the left side, when the mass mu1, added mass of water, less than mu2, we will have the real roots. For this, we will have the exponential decisions. So this is two decisions appropriate to the real roots. And this is the exponential decisions. I'm sorry. These are all two are for the imaginary root. Sorry, this is also sinusoid, and this is the final diagram. How it looks like. Easy to understand the shape of the diagram. This is like a surface due to the argument of the diagram is the two-dimensional. So on one axis we have time, on another axis we have the range of the variation of parameter of proportions of two added masses. On the left side, for this considered range of the parameter, we have the real numbers. I'm sorry, trigonometric form of decision, the imaginary roots. And for this one, right side, we have the real roots and another shape of the decision of the equation of the ship motion with not controls on the surface. So a little bit about the possibility of the proportion between the added masses of ship. Is very specific both. It could be possible, yes. Here we have two examples performed on the figure 12.5.3. On the left side is a historical battleship Novgorod. This is a very circular ship. We can assume that for the ship, perhaps the mu1 and mu2, the added masses of water when the ship moves with acceleration along the abscissa axis mu1 and along the ordinate axis mu2 will be equal to 0 due to the shape of ship. Case is circular. It was the ship constructed in late of 19th century. In the late of 19th century, and as well, not circular could be. For example, it just ship sizes like a length and breadth. For example, maybe for the multi-hull vessels, if the sizes are comparable, perhaps for this ships like maybe floating, the semi-submerged, the floating platform. For example, the ship not stationary but floating platform, and could be that the proportion of the masses of the inertia of water when the ship moves forward with acceleration and the sideward with acceleration have to be close to 1. So the possibility of the middle one magnitude of the parameter for this diagram is possible, yes, maybe, but when the these two moments of the inertia, two added masses of water as a characteristic of inertia of ship in the water will be comparable. So we will be close to this one straight line. This is we can say the line of the demarcation of prerequisites. If we have the smaller is the smaller, which for the majority of ships is perhaps is characteristic. The smaller added mass when the ship moves with acceleration longitudinal, and this is the added mass when the ship moves with acceleration characteristics of the inertia when the ship moves with acceleration transversal is if mu1 is smaller than mu2, the roots will be of the real magnitudes. That's why we have one prerequisite that the decision of the differential equation of the ship motion with not controls on surface is of exponential type. And if we have the imaginary roots, if, for example, the added mass when the ship moves longitudinal with acceleration and when the ship moves transverse with acceleration, when this fraction will be less, will be more than 0. That is when we will have the imaginary roots. In this case, of the equation, this is due to the considering the first factor under the root of the numerator of this formula for the characteristic equation. In this case, we will have the trigonometric decision of the differential equation of the ship motion on surface with not controls. So what does it mean? That means that the ship with the hydrodynamic shape and the ship length is much bigger than the ship width. Usually, the ships are not stable on the course, and with not controls, the ships of usual classes, of usual shapes, tends to rotate when it moves with not controls, tends to rotate transversely to the direction of the motion, and only the ships of unusual types can be stable on the straight line with not controls. Yeah, but the controls required to keep the ship on a straight course on the straight. That's why we have to. And as well, would be of the interest of theoretic interest. The consider the shape of this God diagram within the vicinity of the small time period. When we have the just some seconds, maybe 5 seconds of the ship motion with not control, what could be the shape of the this diagram due to the diagram is characteristic of the ship mechanics of the motion on the surface of water with not controls. And this is interesting for this definite one types of the diagram, the exponential as a decision of linear homogeneous equation of the ship motion on the water, and the trigonometric depending on the inertia correlation of the ship when it moves in the water, longitudinal or transverse. How do the demarcation of the prerequisites impacts the physical properties of ship? Due to this is a physical property of ship. The ability of the ship is not controlled to keep the straight motion. It can appropriately keep the motion, but not the straight, but with the accelerations. This self-acceleration of ship when the motion of ship is not reduced due to the resistance. The velocity of the ship motion is not reduced due to the resistance. It keeps move keeps moving, the ship keeps moving, but at the same time, the ship performs the self-accelerations when the correlation between the added masses of the ship and the water due to the ship shape of submerged volume is more than one, that for the longitudinal, the proportion in the numerator we have longitudinal mass and the transverse mass of the added water. If this proportion more than one, so we have the ship motion is a definite range of the oscillations, but this is a self-oscillations of ship. This will gradually reduce if we do not have the propulsion. But if the ship keeps motion, it with not controls, it keeps oscillates, so it performs self-oscillation. In this case, the ship moves to the another location relative the direction of its motion. So as originally we assumed that the ship moved along the longitudinal axis associated with the ship, that is abscissa axis. So if we have another one proportion, that is the added mass of the ship as a characteristic of inertia, added mass of water associated with the ship motion with acceleration along longitudinal axis, divided to the added mass when the ship moves with acceleration along the transverse axis. When this less than zero, ship tends to lose the course, to lose the direction, and to become move transversely. In the transverse location of ship, relative the initial direction of its movement, the ship in this location transverse relative to the direction of movement, the ship will keep moving directly in this direction, but with accelerations, with self-oscillations. With self-oscillations, the ship will move. That's what is the physical properties of ship with not control. And when we consider a small vicinity of time, this up to 3.95 seconds, 3.6 seconds, we can see that on the functional surface indicated here, this is just a part in the vicinity from this one diagram, but for the very small time period of the variation. And for a short period, about 5 seconds after the moment of initial conditions, the following are indicated as a similarity of the graphs of the angular velocity of ship turn without control and the bifurcation line of the zero values of root of the characteristic equation. So this decision on the left from this demarcation line of the equality of two added masses, this is for the parameter on the horizontal axis of the parameter that corresponds to the equality of mu1 and mu2. So we consider that we have the characteristics of ship inertia when it moves along the longitudinal and transverse axis. These characteristics of inertia are equal, and on the left we have the trigonometric decision for the imaginary roots of characteristic equation. On the right we have the exponential decision for the real roots of the characteristic equation. And for the small range of time considered from the beginning of the initial conditions we assumed, we can find that the shape of the diagrams are almost equivalent. So this differs only after a long time period. So the ship, when the mass, added mass, mu1 is more than mu2, this is like a ship of the indicated examples, or equal to the mu2 if the ship remained the self-oscillation moving in the same direction. If the ship of the usual shapes, when the ship length is much more than ship breadth, is much bigger than the breadth. So for the usual ships, it with not controls will lose the course and will move the course's direction of the abscissa axis associated with the ship, angle between this abscissa or the abscissa axis associated with the ship with a fixed Cartesian coordinate system abscissa of the axis. So originally they coincides, but if the ship change the course, the angle between the axes, so longitudinal axes of abscissas associated with the ship, and the angle arises between the fixed coordinate system and the moved coordinate system associated with the ship. So it turns on the, any side, and after that it keeps the moving in the same direction as each was originally for the initial conditions, but in this direction, yeah, just the opportunity of the movement depends on the dissipation of the energy, and do the motion of the ship attenuates, or perhaps this motion will keep, as for example, if the source of the energy to keep the motion remains. In this case, turning transfers due to the direction of the motion, ship will keep moving with the self-oscillations. This all with not the control if we do not have the feedback system of the ship keeping the straight course. So what the formulas? Theoretically, the decisions of trigonometric type and decision of the exponential type originally looks the same, and the differences arises with the time. Questions and comments. Seaworthy property of ship controllability covering its straight line motion stability is its turning ability under the influence of the control system and the maneuverability, not related to control system, the ability of the physical ship to perform maneuvers under certain velocity. Ship controllability is one of usually considered 5 ship seaworthiness properties, along with buoyancy, stability, and the ship the propulsion property, propulsion performance, and the ship unsinkability, if we consider this property of ship, of partially damaged ship to remains the properties of the buoyancy and stability. So we have, along with the force, indicated the 5th seaworthiness property, the ship controllability is not generally only the performance of the ship with a feedback control system and with controls, but the ship itself. Adopt ship itself have the definite properties due to their controllability. 12.5.2 elements of ship shape having uniformly an opposite effect on stability on course and on ship turning ability when, for example, the ship motion and stability on course improve by increasing the ratio of the length of the ship to brace, ship length to brace, or installing the fins in front of the rudders at the same time can proportionally worsen the ship turning ability. Yes, if the ship controllability performance depends on the components, on the elements, as a opportunity or the possibility of ship to keep the straight trajectory in the ship, on the contrary, the ship possibility to do the maneuvers to turn. So these properties, separate parts of the controllability, can contradict each other sometimes, and the elements, what does it mean? This means that any elements related to ship controllability, like the ship shape, for example, impacts otherwise on the ship each of 2 ship components of the controllability. So on one hand, the definite element can improve the stability of ship on the straight line. At the same time, this worsens the ship opportunity to fulfill the maneuvers. So this is the very contradictory properties, the controllability To reduce this contradiction within the controllability property, one can by the use of the controls with a feedback system. This makes it possible to adopt the appropriate controllability of ship with the contradictive properties in it, as the stability on the straight line and the possibility of ship to fulfill the maneuvers. 12.5.3, the property of maneuverability of physical ship is dependent on control system and on the presence of feedback in it. Is a ship ability to perform maneuvers with definite velocity. It is interesting because the ship maneuverability is not the same as the ship turnability. So the ship can do the turns, but the ownership is not the feedback control system possibility to do the maneuvers depends on the ship velocity. So for definite velocities, ship can be not maneuverable, so it cannot do the maneuvers with small velocities. I will not go into deep in this question because, but yes, sometimes when the ship moves very slowly, the ship do not possesses the possibility to do some maneuvers, and just only the minimal definite velocity required for ship to be the maneuverable. This sometimes. So the maneuverability is the opportunity to do the maneuvers. It's not a turnability, because the maneuverability possesses the possibility of ship to fulfill the maneuvers with definite velocity, and this is the maneuverability, the property of ship itself, with not the controls and the control system. This is a property dependent on the ship itself. Exactly, the controls and control systems are used to do the maneuvers, but the possibility of ship itself, the characteristic of the ship shape and the ship mass, etc. 12.5.4, the main controls operating while the ship is translationally moving or under propulsor running. The auxiliary controls operating without the ship motion or at low velocity, the increase of the main controls efficiency when increasing the ship velocity and reducing the effectiveness of ship auxiliary controls. And it's known that the ship controls, we consider the main ship controls as which required the ship longitudinal velocity. Is not the velocity, the main ship controls are not active. So, and on the other hand, the auxiliary controls, like any kind of the auxiliary devices, as a propellers, auxiliary propellers in the channels, transverse, for example, they are most effective with not the motion of the ship, but when the ship velocity increases, the activity of the auxiliary devices reduces. 12.5.5 types of steering devices of ships: the rudders, multi-blade steering complexes, the rotary steering devices, reversible steering devices, water jet ships, etc. This is just a question as for the for considering the expert overlook, yes, in the technical gears and the technology of the operation of ship control. Types of propulsion and steering devices: the propeller and the rotary nozzle in combination with the stabilizer, the rotary steering column, and the azipod, wind, propulsion, etc. Some steering devices of ship combine together the functions of the propulsion and of the control of ship. This the example indicated in the question 12.5.6. 12.5.7, a system of equations of three projections describing the plane motion of ship on the surface in still water, integrating the equations in the coordinate system associated with ship when determining the velocities, translational, angular, and the accelerations of ship, and finding the translational angular displacements in fixed coordinate system. As we determine in the associated with the ship coordinate system, inertial coordinate system. We do determine the accelerations and velocities. On the next, we can find the ship function of the trajectory of displacement and angular displacement, translational angular displacement. Having the velocities got in the associated with the ship moving coordinate system. So the next, the elements of the trajectory we can find in the fixed coordinate system. Considering the once derivatives got in the moving coordinate system associated with the ship. 12.5.h, assumptions of ship symmetry relative to diametral plan and to midship section plan of time invariance of the velocity projection on the abscissa axis associated with ship, as well as of ship breast smallness compared with its length, and the simplification of system of equations describing the ship motion in still water. To decide the system of the differential equation of the ship motion on the surface of still water with controls or with not controls, this is logical to adopt definite prerequisites as just assumptions. Assumptions can be that like indicated here in the comment, that the ship longitudinal velocity is constant. That is why the time derivative of longitudinal velocity have to be 0, and that the ship is of the symmetric shape, and the ship have the transverse sizes like breast and draft uncomparably smaller than the length of the ship. This concept of symmetry and the proportions of ship and the constants of the longitudinal velocity makes us possible to reduce the difficulty and to simplify the decision. That's why we can have the isolated two differential equations instead of 3 interdependent equations. It's easy to decide with definite assumptions to find the velocities. First, the angular velocity of rotation of ship around the oblique axis. Next, the transverse velocity of ship motion along the ordinate axis. And after that, having these velocities, we can find ship trajectory. If we have constant longitudinal velocity, we will have the diagram or just the decision, analytical decision of the transverse velocity of ship, and we will have the analytical decision of the angular velocity when it rotates around the oblique axis. Next, we can return back to the fixed coordinate system and to have the ship trajectory shape. 12.5.9, transformation of system of two first-order linear equations into one second-order linear equation, which solution serves the solution of equation system describing the ship motion in still water. After the simplified assumptions, we first have to do the transformation with the two got isolated equations. The first transformation is that we have to differentiate the first equation, and we'll find the first derivative of the translational velocity of ship, dependence on the elements of the ship motion with not controls. And no, we do not have the derivative from the first equation. We will just derive the velocity, the derivative from the first equation. And next we have to do the differentiation of the second equation and substitute the first derivative of the velocity got from the first equation into the differentiated second equation of these two isolated motions considered in the one system of the equations. After that, we will have the inhomogeneous second order differential equation relative to the angular velocity of the ship rotation around the oblique axis, the plane rotation on the surface of ship in the water. This could be homogeneous or inhomogeneous, depends on what is the right side of the equations. Do the right sides course as well the driving forces or driving moments. 12.5.10 finding the angular velocity of ship rotation relative to vertical axis of the applicant when it moves in still water by solving linear and homogeneous equation in the form of sum of general solution of corresponding homogeneous equation and the original homogeneous equation particular solution, which is sought in the same functional form as the right side of the inhomogeneous equation. In the considered article 12.5, we do consider only the decision of the homogeneous equation for the ship motion with no controls. Yeah, and this decision, but the general decision of the inhomogeneous equations of the ship moving with the controls on the surface or with the driving forces on behalf of the rudders, steering devices, and propellers. In this case, we general solution will be in accordance with the Cauchy problem. Will be of two summands. The first summand is a general solution of the homogeneous linear second order equation, differential equation of the ship motion, due to the we consider the element of the ship as a function on time of the angular velocity of rotation of ship around the applicant axis. And the second summand in the general solution of inhomogeneous equation will be the particular solution of the inhomogeneous equation. For the particular solution, we have to have the assigned the driving forces and moments, and we have to search the particular decision of inhomogeneous equation in the same form of the dependence on time as the right side of the inhomogeneous equation. Having this type of the decision of the particular decision of the homogeneous equation, we can do the differentiation, have to find the required derivative to substitute on the inhomogeneous equation, and next decide the inhomogeneous equation having this derivative substitute. This we can do perhaps with the use of the complex amplitude approach and the complex number concepts of the decision of the so originally we have the exponential form of the decision and the real numbers, and the trigonometric form of decision of the real numbers, and the assigned driving forces in the moment we have in the real functions, real numbers on the reals. But the decision could be of the complex form, and the process of the decision, and the final result of the decision will be in as well as assigned in the trigonometric or in the exponential form in the real numbers. So just only the process will be of the complex numbers of finding of the particular decision of inhomogeneous equation when finding the element of the ship motion on the surface, like the angular velocity of ship rotation around the applicant axis with the controls, as we are talking about the general decision of the inhomogeneous equation, consistent as well the particular decision of the inhomogeneous equation. 12.5.11 the roots of characteristic equation for the general solution of a homogeneous equation depending on real or the imaginary form of the roots when determining the function of the angular velocity of rotation of ship movement by inertia without the work of propulsors and controls, the exponential and trigonometric forms of solution, and an assessment of ship motion stability dependent on the characteristic equation roots number forms real or imaginary. And so when deciding the homogeneous equation of the ship motion with not controls, the roots of the characteristic equation could be of the real or of the imaginary nature. This depends on the correlation of the inertial characteristics of the ship, translational motion on the surface along the longitudinal axis or along the transverse axis indefinite range of the correlation of the eddied masses as a characteristic of the ship inertia when it moves with acceleration by the longitudinal axis and when it moves by the transverse axis. This impacts the root of the characteristic equation. And if the root is imaginary, we next have the type of the decision of homogeneous equation for the imaginary as the trigonometric type of decision of homogeneous equation. And if the roots are of the real numbers, this is when the inertia ship in water when it moves longitudinal, and the inertia more than inertia on subwater impact when the ship moves transverse, which is characteristic for most ships of the usual shapes of the submerged part when the length is much bigger than the breadth. In this case, we will have the imaginary roots. Excuse me, we will have the real roots of the characteristic equation, and the decision will be of the exponential shape. And this means that the ship will lose the straight course and with not control, and will occupy the motion direction, the same motion direction, but in the transverse location of the ship itself. The ship will move until the motion attenuates, but all due to the attenuation of the motion, I'm moving the ship sidewise when it turned aside to the direction of the motion. The ship will keep the self-oscillations until the total attenuation of the motion of the ship. 12.5.12. An exponential form of general solution of homogeneous equation of the root of characteristic equation is a real number when the eddied mass during the ship motion in water with acceleration of the abscissa is less than the eddied mass of water when moving with acceleration of the ordinate axis, the unstable motion of the ship, and its tendency to turn across the motion direction and then move towards the side, performing self-oscillation. That's what we are talking about, independence of the ship, shape of the submerged part of the ship case. Yeah, for usual ship, they do the turn across the motion direction and then move towards the side, performing self-oscillation. This characteristic. To exclude this possibility and to keep the straight course is required for the usual ship to use the controls and the pilot or feedback system of the controls to keep the direct. And this characteristic for the ship, tendency to turn across the motion direction and then move towards the side, performing self-oscillations, is the property of the ship shape, of usual ship shape. 12.5.13. Trigonometric form general solution of the homogeneous equation and the self-oscillation of limits of ship motion if root of the characteristic equation is imaginary number when the eddied mass when the ship moves in water with acceleration along abscissa greater than the eddied mass when moving with acceleration along the ordinate axis and self-oscillations of ship motion elements. In the different than in the previous question, correlation of the eddied masses of the ship inertia, extra inertia in water than in the previous one question. So when the impact of water on inertia of ship translational motion with acceleration along the abscissa axis is more than the inertia moment, inertia eddied characteristic of the mass when the ship moves with acceleration along the ordinate axis. In this case, the ship is of the ship obey the direct motion with self-oscillations. That is not a very characteristic due to the fact that the ship shape do not correspond to indicated characteristics of the eddied mass. For the usual ship, it is more likely the particulars equivalent to the 12.5.12 question. 20.5.14. The ship motion and different stability with zero roots of the characteristic equation and the continuation of ship rotation with initial angular velocity relative is the applicant. For the ships of very rare shapes, like maybe circular shapes, like we consider the historical ship Novgorod, also the circular shape of the water lines. It is possible that the ship will keep the same direction as the initial one, and they will keep the same angular rotation if it has initial angular rotation, which will keep the motion in the water with the same direction due to the with the same angular rotation due to the reason that the ship added masses in the water in the motion with acceleration in the longitudinal direction are comparable with the added masses when it moves with acceleration in the transverse direction. Due to after the decision of the equation, we can have the indifferent stability of the ship, and we will have the zero root of characteristic equation. 12.5 or 15, the vicinity of bifurcation, a line corresponding to zero values of root of the characteristic equation, which delimits the prerequisites when the added mass during the ship motion in water with acceleration along the ordinate axis is less than the added mass during the ship acceleration along the abscissa axis, and the root of the characteristic equation is an imaginary number, and vice versa. When the added mass is greater when the ship moves with acceleration on the ordinate axis, and the root of the characteristic equation is real number. That is theoretical concept that when we consider a very short time period after the initial conditions, we can find that the shape of the diagram of the ship motion with the imaginary roots of the characteristic equation, the shape of the diagram could be about the same as for the ship with a real number decision of the characteristic equation, real number roots, and these roots depends on the correlation of ship properties of the inertia in the water. Correlation when the ship moves with acceleration along the longitudinal axis abscissa, and moves with acceleration of the transverse axis of ordinata. So we have on the diagram, if we consider the diagram as with two arguments as a surface of the function, the graph of the surface of the function, we consider the demarcation line. So, but it divides the area of definition of diagram of the decision of the homogeneous second order differential equation into two parts. One part we have the exponential decision for the imaginary roots, for the real roots of the characteristic equation, and we have the trigonometric shape of the diagram for the imaginary roots. But considering the very small time period, these look like the same diagrams, like the same decision. Just only difference arises due to the time of the ship motion. 12.5.16, attenuation of amplitudes of elements of ship motion. The angular velocity of turn and transverse translation velocity. When the characteristic equation input factor, the ship translated velocity decreases along the abscissa axis when the ship moves by inertia. That's when the kinetic energy is spent probably by ship inertia motion. That is that the source of the energy for the ship motion when it moves transversely or moves by the angular around as a rotation around the vertical axis when it moves on the plane the source of energy is kinetic energy of the ship motion originally. So while due to the attenuation of the ship velocity, the kinetic energy reduces, the ship oscillations reduces as well. Thank you.